When students first encounter quantum mechanics, they are handed the Schrödinger wave equation. But this famous equation offers only one specific perspective on quantum reality. The native language of the quantum universe is the discrete geometry of linear algebra, rather than continuous calculus. To understand this shift in perspective, we can look to David J. Griffith's Introduction to Quantum Mechanics. The text outlines a rigorous transition from wave functions to vector spaces. Traditional wave mechanics relies on continuous differential equations. Linear algebra utilizes discrete abstractions, matrices, and vectors. This continuous wave approach is historically anchored to Erwin Schrödinger, who formulated his equation in 1926. At the same time, Werner Heisenberg developed an algebraic alternative, matrix mechanics, that removed wave functions from the calculation entirely. By abandoning calculus and embracing Hilbert space geometry, we solve the quantum harmonic oscillator by analyzing the algebra of its operators. In this geometric framework, an operator, t hat, acts as a linear transformation. It maps an initial vector, alpha, into a new vector, beta, by stretching and rotating it. To compute this abstract geometry, we lock it to a set of orthogonal axes, known as a basis. Choosing a basis represents the abstract transformation as a grid of numbers, a matrix. Each matrix element, T sub ij, is the inner product of basis vector E sub I, the operator T, and basis vector E sub j. Notice the geometry of each column. The jth column of the matrix tells us precisely where the jth basis vector lands after the transformation. The matrix serves as a numerical shadow cast by an abstract operator onto a specific set of coordinates. This highlights the concept of basis dependence. Even when we shift and rotate the underlying grid lines, the physical arrow remains untouched. The exact same physical operator results in different matrices depending on the chosen basis. We translate between these grids using a similarity transformation. The new matrix, T sub f, equals S times T sub e times S inverse. The matrix S functions as a mathematical dictionary, translating coordinates between the two systems. Despite these coordinate changes, certain properties of the operator remain identical. Specifically, the trace and the determinant are invariants that do not depend on the basis. We identify these invariants by solving the characteristic equation for eigenvectors. These are the geometric axes that stretch by lambda, the eigenvalue, but never rotate. In quantum mechanics, these invariant geometric eigenvectors correspond to stable, stationary physical states. We bridge this geometry to physics using the notation developed by Paul Dirac. Look at the translation. An abstract vector is the physical quantum state, or the ket psi. Linear transformations map directly to observable operators, like position, momentum, and the Hamiltonian. Hermitian matrices guarantee real eigenvalues, which correspond to observable physical quantities we can measure. Matrix elements are defined as Q sub mn, the inner product of the bra, the dual vector, the operator Q, and the ket. This outputs a complex probability amplitude. Dirac notation calculates these probability amplitudes using pure geometry, removing the need for spatial coordinate systems. Consider the harmonic oscillator. Classically, its Hamiltonian is p squared over 2m plus 1/2 m omega squared x squared. In the quantum version, we replace p and x with their operator counterparts. Our objective is to find the eigenvalues and eigenvectors of this operator purely algebraically, without resorting to differential calculus. To do this, we define two new tools, the creation operator, A+, and the annihilation operator, A-. We express these as linear combinations of the position and momentum operators. The critical relationship is the commutator, A- times A+ minus A+ times A- equals 1. Because matrices do not commute, the order of multiplication dictates the physical outcome. Factoring the Hamiltonian into h bar omega times the quantity A plus A minus plus 1/2 allows us to solve the system without wave calculus. Since a system cannot have negative infinite energy, there must be a ground state. Applying the annihilation operator yields 0, defining the bottom of our ladder. Plugging this into the factored Hamiltonian solves for the ground state energy, E0 equals 1/2 h bar omega. We build the higher energy states by applying the raising operator, A+. Each application of the raising operator generates a new eigenvector, increasing the eigenvalue by exactly 1 unit of h bar omega. This repetitive algebraic application identifies the entire family of stationary states without solving a single differential equation. We arrive at the generalized energy spectrum, E sub n equals n plus 1/2 times h bar omega. The perfectly spaced, discrete energy levels of the quantum oscillator emerge as a geometric consequence of matrix commutation relations. A common professional misconception involves confusing a matrix for the operator it represents. As we see here, a continuous wave function and a discrete diagonal matrix can represent the exact same Hamiltonian. The operator is the invariant physical entity existing in Hilbert space. The matrix is a coordinate representation, dependent on the observer's choice of basis. We have used vector geometry, basis transformations, and algebraic commutators to solve a quantum system through its underlying structure. This algebraic framework scales to 3-dimensional oscillators and the Heisenberg picture of time evolution. Mastering this algebraic translation provides the framework for understanding all advanced theoretical physics, from quantum field theory to solid-state systems.